All right, so now we're going to look at the differential equation dy dx equals y squared plus 4. And this is an example of what we call an autonomous differential equation because the derivative of y only depends on y itself. It's not related to the independent variable. And it turns out there's some nice properties of autonomous differential equations that we can talk about as the course progresses. But for now, we just want to be able to solve. So if you remember how a separable differential equation behaves, this is more or less the same thing. So what we want to do is get all the y's and the dy's on one side. We want to get all the x's and the dx's on the other. So I'm going to divide both sides by y squared plus 4. I'm going to basically multiply both sides by dx. We know that's not technically a valid operation, but it turns out that the way differentials are defined, it actually does work out. So at this point, we have differentials on both sides, which means to get rid of those differentials, we integrate both sides. So I'm going to impose an integral sign on both sides and just integrate both sides now. So the right-hand side is the hardest part, that's x, and I'm going to write plus a constant. A useful result you might remember from calculus is that the integral of dx over x squared plus a squared is equal to 1 over a times the arctangent of x over a. And there normally is a plus c there, but we already have one in our equation, so I'm not going to write it. So in this case, a is 2 and x is basically y, so we're just replacing x with y. So what this gives us is 1/2 arctan y over 2. Now, we often want to solve it for y because y still is understood to be the dependent variable here, right? So we're going to solve this for y using our algebra and trigonometric skills. So first thing I'm going to do is multiply both sides by 2. So that's going to give me the arctangent of y over 2 equals 2x plus 2c. Now I'm going to keep that 2c there for a while because I want to prove a point later. To get the y isolated, we're going to have to take the tangent of both sides. So I'm going to say that y over 2 is equal to the tangent of 2x plus 2c. And that means that y is equal to 2 tangent 2x plus 2c. A lot of 2's in this problem. Now that would be perfectly fine as a final answer, but I do want to highlight one thing, pun intended. This 2c right here is actually just a constant, right? So if c were a half, that 2c would be a 1. So the idea is that whatever my c ends up being, it's going to end up just being another constant anyway. So one might say that a more elegant solution, for lack of a better word here, I'm just going to call it C1 or whatever, or you could just use C all over again, but that's a little confusing. So basically every solution has the form y equals 2 tangent of 2x plus some constant that just fills in the blank, okay? So that's our final solution, and that's an autonomous differential equation, very close to separable, but just a little bit of a twist because there's no x's in it. So we'll just have to see how that plays out. So thank you so much for watching, and watch out for more videos.